Unit 3. We'll start with two vocabulary terms, intramolecular forces and intermolecular forces. Intramolecular forces refer to the forces that bind together the atoms within compounds, whereas intermolecular forces mediate interactions between molecules or compounds. At the top here, we have a molecule of HCl, hydrochloric acid, and another molecule of HCl. You can see that the bonds holding the two atoms together are intra, and the bonds between the atoms are intermolecular forces. It's important because intermolecular forces are responsible for all phase changes. So the homework will have some questions about melting solid to liquid or evaporating liquid to gas. Adding energy increases the motion of molecules until they overcome these intermolecular forces that hold them in place. And that's what allows a substance to change phase, right? When water solid, right, ice melts, it does not break apart into oxygen and hydrogen atoms. It's still H2O. So what breaks apart is the intermolecular forces. There are four main types of intermolecular forces you will need to know. The first is dipole-dipole attractions, and this occurs between the positive end of one molecule and the negative end of another. It only occurs with polar molecules. So it will be your job to look at a formula for a molecule, know if it is polar, and if it is, then you know that it is capable of forming dipole-dipole attractions. Here are some examples of some polar molecules. You're aware of HCl, where the Cl side of the molecule has a negative dipole moment, and H3, where the side with nitrogen, and this third molecule, where the side with chlorine has a negative dipole moment. So any of these molecules can be attracted to another one of itself, another HCl, where the negative side is opposing and the positive side is attracted, or one of these molecules can be attracted to a different polar molecule, right? Because they both have a positive side and a negative side. So any molecule that is polar can have dipole-dipole attractions. The second type of intermolecular force you need to know is called hydrogen bonding. It's an especially strong type of dipole-dipole attraction. That's kind of important. In this type, the highly electronegative fluorine, oxygen, or nitrogen is bonded directly to a hydrogen within a molecule, and any molecule that contains an F, an O, or an N directly bonded to an H within the molecule, that molecule is capable of hydrogen bonding. I like to remember the fun little trick. H with FON can hydrogen bond. If an H is with a FON, fluorine, oxygen, or nitrogen, then that molecule is capable of hydrogen bonding either with itself or with other molecules that also have H with FON. Here we have an image of water molecules. Can it hydrogen bond? Oxygen and hydrogen are directly bonded together. So within the molecule, H is with one of the FONs, F or O or N. So yes, water can hydrogen bond. And the hydrogen bonds are these attractions between the negative side of one water and the positive side of the other. But this type of attraction is particularly strong. It's not just a dipole-dipole attraction, and here's why. Because the highly electronegative difference between hydrogen and one of those really electronegative elements, F or O or N, maximizes that dipole. It makes this a very polar molecule, not a minimally polar molecule. Also, Hydrogen's small size allows for it to get really close with the fluorine, oxygen, or nitrogen. The two can get very close, and that helps them form a particularly strong polarity as well. Sometimes students ask, well, what about hydrogen bonded to chlorine? Chlorine is very electronegative, but chlorine's too large, and so it doesn't make a extremely polar bond the way that H with Pon does. So molecules with hydrogen directly bonded to chlorine, they do not have enough polarity to hydrogen bond. Here is some evidence. We see a graph with period number and boiling point. Why boiling point? Remember, overcoming intermolecular forces allows molecules to separate and turn from a liquid to a gas, that is boiling, or to turn from a solid to a liquid, that is melting. So what we see in this graph is that substances with very high boiling points, like water compared to these other substances, are substances that can hydrogen bond, because the H with the O bond is so electronegative that one water molecule strongly sticks, strongly adheres, is strongly attracted, forms a very strong intermolecular relationship with another molecule. So if we have several waters, they really resist breaking apart, and it's difficult to boil them. The same is true for hydrofluoric acid, because it has H with F, and this ammonium, because it has N with H. Now, these are the trends we actually see. These are the trends we would have expected to see based on their placement in the periodic chart. And when we look at H bonded with carbon, we see that its boiling point is actually quite low. That's methane gas. So it's a vapor even at room temperature. So it certainly has a very low boiling point. Water is a molecule that we care a lot about. It's so important in nature and in health. And here are some of the results of water's ability to hydrogen bond. These are valuable things to know in many sciences, not just chemistry. Water has a relatively high boiling point. Of course, we use it to cool many things, equipment, our bodies. Water has a high surface tension. That basically means the molecules are sticky at the surface layer. They are resistant to breaking apart, and that is because they can hydrogen bond. It exhibits capillary action, meaning that it rises spontaneously up a narrow tube. And again, that can be explained by water's sticky nature. The molecules hydrogen bond, and each H2O sticks to its neighboring H2O very strongly. Finally, water has a high specific heat. That means it takes a lot of energy to raise its temperature. So it's even resistant to the approach of breaking apart. So the temperature raising that occurs before the phase change occurs. There are two more intermolecular forces that we need to know for this unit. The next one is called London dispersion forces, or van der Waals forces. That's another name. Now, these are really weak attractions between molecules with instantaneous dipoles. So just for an instant, it occurs in all molecules. Every single molecule has the capacity to do this, whether it is polar or not. And it's important to note that larger molecules have greater London forces. So what does an instantaneous dipole look like? Well, even a molecule that's not polar can, for an instant, have an uneven distribution of electrons. Here we have a helium atom, and for this very instant, both of its electrons are on the left-hand side because they're always moving, and in any instant, it could possibly have a more negative side and a more positive side, even though the atom itself is totally neutral and it is not polar. But that can happen when something else with a charge comes nearby. It can instantaneously dipole. It can instantaneously create that dipole in the molecule. And it can just happen spontaneously. Imagine an element that has 50 electrons. So that is a very large element, 50 electrons. Those electrons are all moving, but at any given time, there may be 26 electrons on the left and 24 electrons on the right. Well, that instant would give that element a polarity where its left side is slightly more polar than its right. So it can even happen randomly, but it is more, the forces are larger in larger molecules. The fourth and final intermolecular force is called electrostatic attractions. These refer to the very strong attractions between ions, and these occur within and between ions. So here's a little trick. Between ionic compounds, we call them electrostatic forces, but within a compound, we call them ionic bonds. So unfortunately, these two words are often used interchangeably. Ionic bonds are electrostatic forces. Ionic bond is the name, electrostatic force is the type of force that occurs within that bond. Here I have a picture of a lattice, right? Cations and anions, sodium and chloride. If I copy and paste another lattice identical to this one right next to it, those two will stick together, right? The first one, the second one, they will come together. And what will hold them together? Electrostatic forces or ionic bonds. Unfortunately, those terms are often used interchangeably. So it's helpful to note, finally, the order of the strengths of the different types of forces. Now, ionic bonds are intramolecular. I know there's multiple names, so let me go ahead and also add electrostatic force. So electrostatic force is the name we use when it's intermolecular, and ionic bonds is the name we use when it's intramolecular. But either way, it's still the strongest force. It has the highest melting and boiling point. These are hard to break apart. They require a lot of energy to separate the compounds, okay? In the order of about 1,000, right? The melting point for salt is about 1,000 degrees. Covalent bonds have a lower bond energy, and when it comes to intermolecular forces, the ones we've learned about today, hydrogen bonding is the strongest of the covalents, then dipole-dipole, then London dispersion forces. So let's take a look at some practice items where we will put these intermolecular forces into use. Identify the most important types of interparticle forces, so intermolecular forces present in the solids of these substances. Most important, that means strongest, right? The most important, the ones that have the biggest impact on how the molecules behave. So what I like to do is use this list at the top and just go through each of the items. So item A, is it ionic? If it is, that would be the strongest type of intermolecular force that it has. Remember, ionics are metals and nonmetals. Barium is a metal. The answer is yes. So it's ionic. It has electrostatic forces. Item B, H2S. Is it ionic? Well, no, it does not have a metal. So we know it's covalent, but between two molecules, is it capable of hydrogen bonding? Well, H with FON can hydrogen bond. This does not have an F, an O, nor an N, so it cannot hydrogen bond. Can it perform dipole-dipole forces? Well, if it is polar, then yes. Can you look at this molecule and tell if it's polar? H2S, it's very similar to H2O, and we know H2O is polar, so H2S is also polar, so dipole-dipole is the strongest intermolecular force. What about xenon? That's just an atom. Is it ionic? Certainly not. It's not a metal nonmetal. Is it covalent? Well, if xenon is bonded to itself, that would be covalent. Can it hydrogen bond? No, H with Pon. Is it polar? An atom by itself being polar? That doesn't make sense. We know atoms are neutral. Finally, all things can experience that temporary dipole called the London dispersion force. So that would be the strongest force for this molecule. C2H6. Is it ionic? Well, no, it doesn't have a metal nonmetal. So we know it's covalent then, and the intermolecular forces we're being asked about are either hydrogen bond, dipole-dipole, or London dispersion. It cannot hydrogen bond. It's not H with Pon. Is it polar? Now, you may need to make a Lewis structure in order to see whether or not this molecule is polar. And it's going to take time. So the quicker you can just imagine it, you will have an advantage. But here's a Lewis structure. Everything has an octet. There aren't any different terminal atoms, no non-bonding pairs on the center. So this is not polar. It does not have dipole-dipole forces, London dispersion forces. Finally, cesium iodide. Cesium is a metal, so this has electrostatic forces because it's ionically bonded. So ionic, that's the intramolecular force. Electrostatic forces, that's the intermolecular force. Unfortunately, those words are often used interchangeably. P4, so four phosphorus atoms clinging to one another. That could be tough to make a Lewis structure for because we don't know if it needs to be a chain or a ring. We know it's not ionic. We know it cannot hydrogen bond. So it's either polar in its Lewis structure or it is not. So either dipole-dipole or London dispersion. Now, I can guess that it's not polar because all of the phosphoruses have an equal electronegativity, and without any further information, that would be a reasonable guess. So I'll go with London dispersion forces for this one. NH3, is it ionic? It is not. So we know it's covalent. Can it hydrogen bond? H with Pon. Give the homework a try.